Hello everyone, and welcome to Week 7 of Abarso's 10th grade math Google Classroom. This week we will be reviewing our competency related to analyzing sequences and series, both arithmetic and geometric. These skills will be assessed on the placement assessment you take upon returning to school. As you follow along, take notes on the examples and definitions that are provided. These will be useful guides and can be used on the short quiz associated with this lesson. If you don't have them with you already, pause the video and grab your pen and notebook before we get started. Let's get started with the do now. What is the relationship among the following numbers? -1, 4, 9, 14, 19, 24, 29, and so on. Pause the video briefly as you determine the relationship. Right, so that should have been quite easy. To move from one number to the following number, we must add 5. In other words, each term has a difference of 5 from the term that precedes it. While we can easily see what this relationship is, let's dive into the mathematical theory that tells us why this relationship occurs. The two simplest sequences to work with are arithmetic and geometric sequences. Let's start with arithmetic. An arithmetic sequence goes from one term to the next by always adding or subtracting the same value. For instance, 2, 5, 8, 11, 14, and so on is arithmetic because each step adds 3. And 7, 3, -1, -5 is arithmetic because each step subtracts 4. You should recognize that the do now was indicative of this type of sequence. The number added or subtracted at each stage of an arithmetic sequence is called the common difference and is denoted using the variable d. It's called the common difference because if you subtract, that is, if you find the difference of successive terms, you'll always get this common value. A geometric sequence goes from one term to the next by always multiplying or dividing by the same value. So 1, 2, 4, 8, 16, and so on is geometric because each step multiplies by 2. And 81, 27, 9, 3, 1, 1/3, and so on is geometric because each step divides by 3. The number multiplied or divided at each stage of a geometric sequence is called the common ratio and is denoted using the variable r. That is because if you divide or find the ratio of successive terms, you'll always get this common value. Let's put this information into practice and solve a problem involving arithmetic sequences. Let's find the common difference and the next term of the following sequence: 3, 11, 19, 27, 35, and so forth. To find the common difference, I have to subtract a successive pair of terms. It doesn't matter which pair I pick as long as they're right next to each other. To be thorough, I'll do all the subtractions. 11 minus 3 is equal to 8. 19 minus 11 is equal to 8. 27 minus 19 is equal to 8. 35 minus 27 is equal to 8. The difference is always 8, so the common difference is d equals 8. We were given the first 5 terms, so the 6th term of the sequence is going to be the very next term. I find the next term by adding the common difference to the 5th term. In this case, 35 plus 8, which equals 43. So final answer, a common difference is d equal to 8, and the value of our 6th term is 43. Let's try an example of a geometric sequence. Let's find the common ratio and the 7th term of the following sequence: 2 9ths, 2/3, 2, 6, 18, and so forth. To find the common ratio, I have to divide a successive pair of terms. It doesn't matter which pair I pick, as long as they're right next to each other. To be thorough, I'll do all of the divisions. 2/3 divided by 2/9 is equal to 3. 2 divided by 2/3 is equal to 3. 6 divided by 2 is equal to 3. And 18 divided by 6 is also equal to 3. The ratio is always 3, so our common ratio, our r variable, is equal to 3. We were given the first 5 terms, so the 6th term is the next term. The 7th term will be the term after that. To find the value of the 7th term, I'll multiply the 5th term by the common ratio twice. So the 6th term would equal 18 times 3, which is equal to 54. Therefore, our 7th term will be 54 times 3, which equals 162. Our final answer, we have a common ratio of r equals 3, and the value of the 7th term is 162. Since arithmetic and geometric sequences exhibit regular behaviors, they have useful formulas that can be applied. For arithmetic sequences, the common difference is d, and the first term is a sub 1. Since we get the next term by adding the common difference, the value of a sub 2 is just a sub 1 plus d. If we were to continue on to try to find a sub 3, our third term, we would get a sub 1 plus 2d. At each stage, the common difference was multiplied by a value that was 1 less than the index. Following this pattern, the nth term, a sub n, will have the general form a sub n equals a sub 1 plus the quantity n minus 1 times d. For geometric sequences, the common ratio is r, and the first term is a sub 1. Since we get the next term by multiplying the common ratio, the value of a sub 2 is just a sub 1 times r. This continues for the third term, which would be a sub 3, which is equal to a sub 1 times r squared. At each stage, the common ratio was raised to a power that was 1 less than the index. Following this pattern, the nth term, a sub n, will have the general form a sub n equals a sub 1 times r to the power of n minus 1. Now that we have a sound foundation of sequences, let's move on to series. Let's begin with arithmetic ones. An arithmetic series is simply the sum of the terms of an arithmetic sequence. For reasons that will be explained later in your math studies, you can only take the partial sum of an arithmetic sequence. The partial sum is the sum of the limited, that is to say, finite, number of terms, like the first 10 terms or the 5th through the 50th terms. You can find the partial sums of finite arithmetic series by using the following formula. If you take the 2 on the right-hand side of the equal sign from under the n and convert it to being a 1/2 multiplied by the parentheses, you can see that the formula for the sum is in effect n times the average of the first and last terms. Thinking of the summation formula this way can be useful for learning the formula. Let's move on to an example to demonstrate the formula in action. To find the 35th partial sum of the sequence described requires us to find the first and 35th terms. In this case, we find a sub 1 to equal 3/2. Given that we're interested in the 35th term as well, we simply multiply our common difference of 1/2 by the 35 and add 1. Using these two values, we can then calculate the sum of the first 35 terms in the sequence, which is 350. Just like an arithmetic series is the sum of the terms of an arithmetic sequence, a geometric series is the sum of the terms of a geometric sequence. For a geometric sequence with the first term a sub 1 equals a and a common ratio r, the sum of the first n terms is given by the following formula. Let's try an example to demonstrate how to put this formula into action. First, it's a good idea to find the values of the variables we need to make the formula workable. Namely, a sub 1, and the common ratio. Knowing that we want to find the 20th partial sum, it's just a matter of plugging these values into the formula and solving. When we do, we get a final solution of 2,097,150, which is the sum of the first 20 terms in the geometric sequence. Now I know we've covered a lot of ground in this lesson, but this should be reviewed given the depth of your exposure to sequences and series in your reasoning class. In order to get an even more practice, the following problems are designed to test your knowledge of the formulas we just studied. Pause the video and try your hand at solving the following questions. Thank you for tuning in. Hopefully you were able to follow along and understand the various ways of solving sequences and series. Check out the links in the description below for further resources to help you master this topic. All of these resources can be used to help you complete the short quiz associated with this week's lesson. If you have any questions or concerns, feel free to reach out via comments in our Google Classroom or via email. We're always here to help.